Thank you. Good morning to everyone. There are two lectures this session. The first one will be delivered by Professor Ralph Turner from the University of Marburg, Germany. He is a theoretical chemist and a computational chemist who specializes in the density functional theory. He has received the Hans Hellman Prize for the theoretical chemistry and the Theoretical Fellowship of it's a German government fellowship, right? It's a Humboldt Fellowship. So with this brief introduction, may I ask Ralph now to do this? The 25 minutes of this.
Working? Yes, wonderful. So, thank you very much, Professor Murugaba, for the kind introduction, and thank you all for coming. And first of all, I'd like to extend my sincere gratitude to Professor Wanza, who's a very valued guest in Marburg regularly in the last years, and I enjoyed all our encounters over the last years, starting from my time as a PhD student in Gernot Franklin Group, where he visited, and becoming really one of our highest valued guests in Marburg. And I always enjoyed your hospitality. And that always gives the next step towards what I'd also like to extend these gratitude and thanks to all the faculty and students and all the people of India I've had the pleasure to meet up to now, because I'm absolutely stunned by this country. It's the first time I'm here, and the hospitality and the beauty of this country definitely will make me come back. So I will already plan my next India trip. With this, I'm also grateful to Professor Berger, because he introduced you already to the topic of theoretical chemistry. And as you see from the numbers that are on my title, I'm also a theoretical chemist. And I will tell you today on how we can use theoretical chemistry in terms of quantum chemistry to learn about surfaces, so about reactions of molecules with surfaces, and especially about how organic molecules react, and that you can use your understanding that you gained in molecular chemistry to transfer this and use this to understand what is actually happening at the surface. You don't need to be the solid-state theoretical physicist to understand surface chemistry, but all you need is your chemical intuition and your knowledge. But first of all, I'd like to briefly introduce you to Marburg, because that is where several of the delegates are coming from, and also several of the esteemed colleagues have stayed in. So Marburg is a traditional German university town, nearly in the middle of Germany, so we're around about here. This is Frankfurt, so we're just 1 hour north of Frankfurt. Everybody knows Frankfurt because that is the biggest international airport. We actually have the oldest chemistry department worldwide, at least by our definition. So we have Johannes Hartmann, who has been a professor of chemiatry more than 400 years ago. And that was not long after the university was founded in 1527. So this is a major site of the university town. We have the Elisabethkirche, which was actually the main reason that Marburg became popular, because we had pilgrimage in the 13th century towards this grave, and then we have a large castle which actually goes back to the 700s and 800s. And this is our new chemistry department. Used to be in a sort of typical chemistry department from the 70s, which is now completely rebuilt. So we are very, very happy to have fantastic working environments in Marburg, and I welcome you all to spend some time there if you're in Germany. With this, I started to talk with the very famous quote of theoretical chemistry, which is attributed to Charles Coulson. He is supposed to have given that in a conference in 1960, where he was urging his colleagues from theory to give insights and not just numbers. So not just sort of compute everything and give huge tables of numbers, but derive the chemical insight that is needed to really sort of make progress and make things easy and deliver new ideas. And since the 1960s, much has happened, and my valued mentor, Gernot Franklin, rephrased this a few years back on a conference in Heidelberg, because he said, give us insight and numbers. because now theoretical chemistry is at a stage where it can make quantitative measurements in terms of computation experiments. So the quantum mechanics and the methods are as accurate that we can use these numbers and try to derive insights from that. And that is the growth that are driving my research. So to give you an insight on sort of an introduction of the topic I want to talk about today, these are typical concepts that you know from molecular chemistry. You learn about chemical bonding, one of the most powerful heuristic concepts in chemistry. You learn about Lewis structures. They are actually more than 100 years old. They go back to Gilbert Lewis, whom we heard about before, who actually proposed this idea in the 1916. And chemists like to think and discuss in chemical bonding terms. We also like to think in terms of reaction classes. You might have heard already in your studies about nucleophilic substitution reactions or other type of typical reactivity that helps us to really make catalogs of what is happening in chemistry, predict new chemistry, and understand what is going on in this huge chemical universe that we are about to explore. I like this expression very much. And the third thing that you might know is the functional group. So you know that an OH group behaves very differently if it's in an alcohol or if it's in an acid group, but you also know that you can transfer these functional groups from different molecules, and you know that they behave rather similarly. If you now go to the field of surface and material science, the concepts are very different. This is due since this field was mostly developed by people with a physics background. So they have a very different look. This discipline has a very different look at things. So, for example, when people talk about bonding on surfaces, they often discuss terms like physisorption and chemisorption, which I will come back to later, which are sort of, for the chemist, often hard to understand because the criteria behind it are not so clear from what we'd like to have, and people often use adsorption energy for differentiating that, which is actually a bit problematic. A bit better it does look like if you go to surface chemistry, there are some of the concepts from molecular chemistry have already been transferred, but if you go one step further to solid-state materials and interfaces, very often people discuss in terms of semiconductor physics or the band structure picture, which is actually not so easy to get into the concept that we'd like to have as chemists. So as a bottom line, I would like to state that the chemical approach, this local view that we have as chemists on electronic structure, is much less common in this field. So this leads to the research topics that are covered in our group. We like to look at molecular structures, reactivities up to surfaces, which I will mostly talk about today, but also material science, some spectroscopy methods, and then especially think about chemical bonding and develop and use tools to understand chemical bonding in very different environments. So the research concept starts from electronic structures field. So this is the engine of the approach. So we use quantum chemical methods, which I will briefly talk on one of the next few slides, to understand molecular chemistry. But then we like to use these concepts of bonding reactivity and transfer them to the world of surfaces and solids. And by this, we often start with the interpretation of an experiment, but our goal is always to go one step further, to really make the theory predictive and derive concepts that give back something to experiment. So first, the engine of this approach. A very general idea on how to theoretically describe chemistry, just as a primer. So we have a nucleus surrounded by electrons, and we can either cover this with classical mechanical approach, so force fields, for example, where we use the classical Newton mechanics, the classical forces, and in this respect we actually neglect the electrons and we only talk about the movement of the nuclei, and the electrons are more or less a decoration to the nuclei. But this is an approach where we cannot describe bond making and bond breaking, so it's difficult to apply to chemistry, although it can be very helpful, for example, for drug discovery. Quantum mechanics is the approach where we actually care about the wave nature of the electron. And here we come to the sort of major equation in the field, the famous Schrödinger equation, where we describe the system in terms of the wave function, which is abbreviated with this letter psi, and we apply a so-called operator that you heard about before in Robert Berger's talk, to derive the quantity that we like to have. So we actually ask with the operator the wave function, and the answer we get is the energy. And this is the basis of quantum chemistry that we also apply in micro. A major approximation here is the so-called Born-Oppenheimer approximation. So we separate the movement of the nuclei and the electrons, and this leads to the famous and often used concept of the potential energy surface. So you might have seen that you move from a starting reactant up to the product over a transition state, and you're only allowed to use this description if you apply the Born-Oppenheimer approximation. And you're usually allowed to do that because the nucleus is much, much, much heavier than the electron, at least 2,000 times or 1,800 times. This is why this approximation is usually very good and allows us to draw this potential energy surface and talk about reaction mechanisms. The method that we're mainly using in my group, and which is the major workhorse in material science and also in the majority of molecular chemistry, is density functional theory. So this sort of equation, the pictorial representation, tells you what this is about. So what we essentially need to know is the electron density. So the distribution of the electrons in the molecule or in the solid or surface material. And then we have a so-called function, which means we put this electron density into an equation and it delivers us the energy. So we have a direct connection between electron density and energy. So this is the basic idea of density function theory, which goes back to Hohenberg and Kohn in the 60s. And there are some terms which are rather easy: the kinetic energy of the electrons, the Coulomb, so the classical electrostatic interaction, the nuclear electron attraction, and then there's a difficult term. And the difficult term is the interaction of the electrons with each other. And this is what we put into the famous exchange correlation function. So if you hear about an exchange correlation function, it's a difficult part of DFT. And this is where all the approximations come in. It essentially controls the accuracy of the computations. Famous examples are E3LYP or PBE, BP86, and so on. If you're familiar with molecules, then you have to make a few steps if you go to the description of materials. First, we don't have a molecule that we represent, but we try to represent a solid. We do this by choosing a unit cell, so a cell which represents a part of our perfect crystal, and then we repeat that in all three dimensions with so-called periodic boundary conditions. If we want to do this on the surface, of course, we don't have three-dimensional structure, but we have a two-dimensional structure. But for technical reasons, we also use the third dimension, and we apply the so-called slab approach, where we describe the surface, and we have vacuum between these so-called slabs. If we do this approach, we leave our familiar field of molecular orbitals, and we have to care for the electronic structure in terms of the band structure, since we have to care about K-space, reciprocal space, and we get these nice spaghetti plots. They look pretty tricky, but Roald-Hoffmann showed us in the 80s already that we can actually understand them with the LCAO-MO approach that we know from molecular chemistry. And for the experts, one of the serious drawbacks in solid-state research in theory is that we're pretty restricted on the methods that we can actually use beyond DFT. The method that we're using in my group to understand chemical bonding is a transfer of a concept which is well established in molecular chemistry. Energy decomposition analysis means that you decompose the bonding energy, for example, in a molecule or between a molecule and the surface, in several well-defined physical-chemical terms, and you can have an interpretation of these terms which tell you about the nature of chemical bonding. And so the energy decomposition analysis is well established in molecular chemistry, and we now transfer this to surface chemistry. So what we start off with is the surface and the molecule in their sort of ground state configuration, and then they need to deform to make actually the bonding. This is the preparation energy that you need to invest. Then we need to cover for one problem in density functional theory, that is dispersion interactions. They are very difficult to describe with most density functionals, so we apply a semi-empirical approach to cover dispersion interactions. Then we have three steps which give us the terms in the EDA. The first is the overlap of the electron density. So it's a quasi-classical electrostatic interaction. It's attractive. Then we need to orthonormalize the wave function in between. That gives us a repulsive step, which covers that we actually fulfill the Pauli principle. and this intermediate wave function is relaxed to the final state, which gives us the orbital energy, which is closely connected to the covalent bonding contribution. This last step is often the most interesting for the chemical interpretation, so we use deformation density to find out what are the major contributions here. And one example from molecular chemistry is the myeloborane, which is shown here. So you see this charge flow from red to blue is the first deformation density of this molecule. And it closely resembles the Lewis structure picture, where we have charge flow from this non-bonding electron pair to the empty orbital. We can get the energy that this interaction delivers actually, and the stabilization energy is quite large for this deformation density. And by this EDA plus this deformation density, which is so-called the NOCV extension, we can get a very good picture of the chemical interactions in the system. So from molecular chemistry, I just very briefly want to mention what we've worked there. Previously, I worked on cabenes and developed together with Björn Franking, the concept of cabones, and there comes the phosphorus into place, since obviously many people are working on phosphorus here. The cabones, or the major example, was the carbodiphosphoRane, where you have a carbon atom and you have phosphine groups on both sides, and we could show that they can actually be described in terms of the donor-acceptor bond of this phosphine ligand to the carbon in the oxidation state 0. Recently, we also worked on carbene complexes from transition metals, reaction mechanisms in different fields, fullerenes together with my postdoc mentor Peter Schweltweger, and gas phase reactivity in thin film deposition processes that I will not talk about today. For the solid state side, just to give you an overview, we're interested in compound semiconductors, of interfaces, but all the way also to molecular crystals and clusters. What I want to mainly focus today is the application to surface science. And here we also looked at different types of surfaces. Metal surfaces are interesting because you can apply all the surface science analysis techniques from experiment, but the semiconductor surfaces are interesting because they deliver a very good picture that can be understood from a molecular chemistry perspective. So why should we care about organic functionalization of semiconductors? If you think in terms of sort of big picture motivation, then you can just have a look at your smartphone. If you are happy enough to have a high-end smartphone, then the display is made out of organic light-emitting diodes. And if you look at this schematically, it's actually an organic semiconductor material which is in touch with metal electrodes and which is in touch with some sort of support, which is an insulator or a semiconductor. And ultimately, the performance of the device depends on these physical-chemical interactions at these interfaces. So we need to know about these interfaces between the materials. And if you want to study them, you need good models, because actually you need a perfect interface, otherwise everything is determined by defects. So how can we get these interfaces? First of all, the surface that we're mostly looking at is the silicon 01 surface I'd like to briefly introduce. So we start off from silicon in the bulk structure, so it's the same structure as diamond. If we now cut along the 001 plane, we create silicon atoms which are very unhappy. Because every silicon atom has these two rabbit ears, which means we cut two covalent bonds and they have two unpaired electrons. This is a very unstable situation. So the first thing that happens is that they form dimers on the surface. So two silicon atoms build one sigma bond here, and they're just left with one rabbit ear, or so-called dangling bonds. That is the surface science language here. So this is still an unstable situation. So what happens is essentially a charge transfer. One electron is transferred from this rabbit ear to the other rabbit ear, and what also happens during this procedure is that one atom moves below the plane and the other one above the plane. And this is a major reconstruction of the surface that is determining the surface chemistry. And the Lewis structure, which can be used to describe this dimer, is shown here. So we essentially have an atom with an empty orbital and an atom with a filled orbital. So we have a nucleophilic and electrophilic reaction center. This explains the rich chemistry of this surface. So if we now want to build an interface from a model interface, we start from this inorganic substrate and we add organic molecules, an organic add layer, and then second and third layer. There are many approaches to do that. The approach that we followed in Marburg from theory and also experiment is using cyclooctane. Cyclooctane is the smallest stable cyclic alkyne. So it's an 8 ring with a triple bond. So it's pretty strained. It's also used in chemical biology a lot because you can make click reactions without the catalyst, but we use it for the surface. And the idea is to have a functionalized cycle of time, which can then be in the next step functionalized with the second layer and third layer and so on, building up an interface. But first we have to understand how the cycle of time reacts with the surface. And of course we are not synthesizing these molecules and the surfaces, but we are interested in the theoretical description. So the challenges that we are facing from theories, we want to understand how do the molecules actually arrive at the surface? What's the adsorption dynamics? How do they interact with the surface? What is the surface bonding? And last, how is the reactivity on the surface? Because that determines what is actually coming up. So we look at cycle of time itself, but also model systems, ethylene as a prototype molecule for unsaturated hydrocarbon, and THF because the ether functionality is one possible functional group for this approach here. So first challenge, adsorption dynamics. If you talk about adsorption dynamics on surfaces, then you talk about precursor stability. Because very often what happens if a molecule comes from the gas phase and approaches the surface, it has an intermediate state, which is called a precursor in surface science. And then it transforms to the final state. And for ethylene, for the model system, this precursor is well known from theory and experiment, and it's sketched here. For cyclooctane, there was indications from our experimental colleagues in Marburg that there's a different pathway, and there might be even a direct adsorption without this precursor state, which would be very unusual because this was not known for unsaturated hydrocarbons before. So let's look at the model system first. If you talk about surface adsorption, you always end up at some stage or another by the picture on the left-hand side, which goes back to Leonard Jones from the 30s. So he described atoms adsorbing on metal surfaces with this picture. So you have a physisorption regime where the atom is actually interacting by isotropic van der Waals interactions with the surface, creating a first physisorbed precursor minimum. And then upon further approach, you have to overcome a barrier before you end up in the chemisorbed final state, which is determined by covalent bonding contributions. If you now look at the potential energy surface, on the right-hand side for ethylene on silicon, it looks qualitatively very similar. So you have the molecule approaching the surface, you have a precursor state, a barrier, and the final state, which is formally a 2+2 cycloadder. What we were puzzled was the description of the precursor state in the literature, because this was described as physisorb. And from our chemist's perspective, this very much looks like a directional interaction between the ethylene and this silicon atom. So already if you look at the orbital picture, so the crystal orbitals, the periodic equivalent of the molecular orbitals, you see an overlap of the orbitals from the molecule and from the surface. Now we can quantify that with our EDA method, and we can get numbers for this interaction. So first we see that the bonding interaction is 70 kilojoules per mole. This is the unit which is common in surface science, and this is a pretty strong interaction. If you consider that you have to invest preparation energy to really make the deformation of the molecule, you have an interaction energy of molecule and surface of more than 100 kilojoules per mole. And now for a physisorb complex, you would expect that this is dominated by dispersion interaction. But this is not the case here. Dispersion interactions only make up round about a quarter of the stabilization energy, but it's mainly the electronic interactions stemming from electrostatic and orbital attractive interaction and set off by the Pauli repulsion. So we have a strong covalent character of the bond here. And the deformation density also tells us what is the major stabilizing factor here. You see this charge flowing from the pi electron region of the ethylene towards this empty surface state. So this is the donor-acceptor bond that we would call a pi complex in organic chemistry. So this is the nature of this bond that we could then determine by this energy decomposition analysis. And we also made a proposal for experiment. We simulated scanning tunneling microscopy pictures, which is a very common approach in this field, and we could propose a picture which is then further found, or hopefully further found in experiments. We also looked at the cyclooctane molecule, and from the adsorption path sampling, we could see that this molecule actually obviously adsorbs in a direct pathway. So there is no intermediate, there's no hump in this potential energy surface. But this is a case where the static calculations that we often do is not sufficient. we have to go to a dynamic picture. So we applied ab initio molecular dynamics, and this really gave a different picture here. Because we saw in some of the trajectories that we actually have an intermediate state here shown in gray, which is a very short-lived precursor state before, with a very low barrier, it transfers to the product. And so we have a 1 picosecond where this precursor state lives, which we missed if we only do the static DFT calculation, and we need this dynamic description to really cover the full adsorption description. So that brings me to the second challenge. Now the molecule is at the surface. How does it bind there? The first example comes from the monosystem tetrahydrofuran. There the experiment had two interesting findings. The first one is that the precursor could become isolated. And this is unusual because these precursor states are usually too unstable and they usually react very quickly. So we computed the bonding energy, and with 124 kilojoules per mole, it's the strongest oxygen-silicon donor acceptor bond which is known up to now in this field. But why is that so strong? And here the bonding analysis gives the answer, because we see two major deformation densities, which are sigma-type donation and pi-type donation from these two non-bonding electron pairs at the oxygen into the MPP orbital, and then we have a high-lying sigma star silicon-silicon bond at the surface. And jointly, these stabilization lead to this species being the strongest oxygen donor up to now and making it experimentally detectable. For the second example of cyclooctane, we had the results from the experimental colleagues from scanning tunneling microscopy, and here they show these white blobs. So these are the molecules, and they saw two features, A and B. B is easy to understand. The peak is on top of the dotted line, so this is in line with the on-top structure, where the triple bond of the molecule attaches directly to the silicon-silicon dimer, like in the ethylene case. But A is harder to understand because the peak is in between the dotted lines. So here the proposal was that we might have the pedestal mode, where the triple bond is in between the four silicon atoms, making formally 4 carbon-silicon bonds. Our computations showed, and are hopefully shown now, that the adsorption energies clearly show that this pedestal mode is very unstable. The on-top mode is by far the most stable and should dominate the experimental findings. So what happens here is that we have a molecule which is rather flexible. It has sp3 hybridized bonds, so it bends over these trenches, and it's not straight up like a stop sign. So if you now think about an STM tip moving along the surface, it will see these atoms here in between, and they look like as if the molecule is sitting in between the surface dimers. And we can really emulate the experimental spectrum, and we find a very good agreement. So we can also look at the bonding here on this question why this on-top mode is so much more stable, although formally we have less carbon-silicon bonds. And if you look at the interaction energy, indeed the pedestal mode is more stable. So this one is more stable than the on-top mode, but of course the molecule and surface have to strongly deform. We find that in the preparation energy, so that the stabilization energy is eaten up and the bonding energy is much lower. And if we normalize it to the number of carbon-silicon bonds, every bond is weaker in the pedestal case compared to the on-top case. So this brings me to the last challenge, the on-surface reactivity. Again, tetrahydrofuran. If you increase the temperature in the experiment, what happens is that this precursor state is attacked by a silicon atom, and you have a bond breaking. This is not so exciting. This always happens. But what is exciting is that it's region selective. So there's only one product where the THF is sort of crossing these two silicon dimer bridges. And we wanted to understand this. Because in principle, there are 3 atoms which could attack the THF, A, B, and C. And if we now look at the reaction energy for this backside attack, then C is actually the least stable one. So energy and even free energies, Gibbs energies, would prefer A or B to attack. So if it's not thermodynamics, then you should look at the kinetics and the reaction barriers. And indeed, this is the explanation. We see that the reaction barrier for the attack of atom C is just half the size compared to A and B. And this nicely explains the selectivity. But it doesn't tell us why this barrier is so much lower. Here comes the analysis and the electronic structure analysis into play. Because if we have a look at the transition state, we see that we have a rather short carbon-oxygen bond for the ether functionality still, and a rather short contact to the neighboring silicon dimer in comparison to A and B. We also have a nearly linear arrangement in the transition state structure, which you can see here. If we now look at the EDA, we also see that we have charge flow from this neighboring silicon dimer into the newly formed carbon-silicon bond, but at the same time, electron density is removed from this ether bond. So we have bond making and bond breaking at the same time during the reaction, and this linear arrangement, and this is very reminding us of an SN2 type reaction. And indeed, this is the first SN2 type reaction at the surface, which has now also been found in experimental investigations of similar systems. So we can understand the real selectivity because A and B are just not able to make this backside attack, so we have an SN1 type reactivity. With this, I'd like to summarize that I hope I could show you that we can use these concepts that you know from organic chemistry, from molecular chemistry, to understand what is going on at surfaces, and you can support this with quantitative electronic structure analysis. And I'd like to thank my group, especially Dr. Lisa Pescher, who did the tremendous work, essentially did all the work that I presented to you today. And with this, I'd like to thank you for your attention. I'm looking forward to discussions and questions.
Thanks, Rob. We may have time for one or two quick questions, very brief. Can I ask you one?
Yes, please.
This assumption that the SA bond is formed and the electron switches from one silicon to other silicon, do you have any experimental evidence for this? X-subs or Zanes?
Sorry, you're talking about the SN2 reaction?
When you cut the silicon got a 101 plane,
yeah.
You said the SA bond is formed and the electron goes from one silicon to other silicon.
Ah, all right.
It creates a W occupied and an unoccupied orbital.
Yeah, yeah.
Can you pick this up using any surface photoelectron?
You can do that with low temperature scanning tunneling microscopy. That is why this surface reconstruction was discovered quite late, because at the usual SDM picture you only see the average structure, because this is a flexible configuration. And so at the room temperature you only see the average, the straight dimers. But at low temperature, below 70 Kelvin roughly, or 50 Kelvin, you see that this movement is frozen out. You essentially see this C4 plus 2.
Yeah, your 129 negative 12 joules per mole probably kind of supports this.
Yeah, so the barrier for this flipping is around about 30 kilojoules per mole, so it can be overcome at slightly elevated temperatures. But the reactivity is really dominated by this buckling, so you barely see reactivity coming from the parallel dimers, which would be more of a radical type reactivity.
Thanks.
Do you think you could extend this theory to nano indentations if you were to do a tapping mode, and if you want to indent a soft surface and then let it come back? So would your theory apply to such type of systems?
Can you give an example of what type of indentations you're thinking about?
So if you have a cantilever, the way you were showing, you have a tapping mode, right?
Yeah.
If you were to tap really thoroughly on a soft surface, and then let the surface pull back again, would your theory of electronic structure and the deformation on that soft surface could be addressed by these calculations?
Yeah, so if you're able to set up a surface model which is sort of small enough that you can tackle it with ab initio theory, then, I mean, what you could do is you could try to get a model for the indented surfaces and the non-indented surfaces, and then get an idea about the energy difference that you need to invest to make this indentation.
The problem would be very initial for it.
Yes.
For the soft surface.
Yeah, so I mean, the problem is that if the system is not possible to be represented by a small unit cell, with small I mean 300 to 400 atoms, then you have to sort of go through different types of theoretical approaches, because otherwise it would be too expensive for that type of approach.
I guess we should close it here. Let's thank once again Dr. Toller. The next speaker is Professor Dr. Ganesh Pandey from the Center for Biomedical Research in Lucknow, where he is director. He is a very well decorated organic chemist from our country. He is the editor for the Tetrahedron Journal. He won several prizes, including Sanjay Bhatnagar Prize, fellow of all the academies, Jesuit Post Fellow, and his area of expertise is in the area in total synthesis of natural products and development of new synthetic methodologies. Professor Pandey. Thank you, Professor Burgwal, for your kind words of introduction. Before I start, I would like to thank Professor Bansal, Dr. Rakhi Gupta, and Ashok Gupta for inviting me to this conference and giving me this opportunity to share some of the chemistry which we have been doing at Lakshmi. Actually, I am a frequent visitor to this university, and whenever Professor Bansal or Rakhi Gupta invites me and asks to give a lecture, I find very difficult because I cannot produce result in 1 year to give a lecture. So I have to really dig out something which is new, and I find something new which is ongoing, and I would like to share this. And this is a completely different than two previous speakers. They have presented the theoretical aspect of chemistry at a very atomic level, or I will present to you a very complex structure and synthesis. This is some of the molecules which we have been working in our lab to synthesize. Let me see. And some of them are completed, some of them are still going on, maybe closer to synthesis, completion of the synthesis. But you would ask here that why do you select such a complex structure to synthesize? Because this is very often young students will think that why one has to spend so much time and difficult structures to make, because it's full of all stereo structures, quaternary structures, ring structures, and so on and so forth. And I have to tell you why do we synthesize the molecules. The total synthesis of a natural product is a driving force for the development of not only synthetic organic chemistry itself, but also drug discovery to improve human well-being. Complex structure of a natural product provides an opportunity to innovate new chemistry for the development and sustenance of this vibrant bunch of chemistry. If we don't have any target, then how the chemistry will develop? So natural products, they provide you targets to innovate new chemistry, drug discovery, and this is the motivation and challenge for young students to understand the nuance of organic chemistry research. Synthetic developments have enabled the design modification of your products, templates in a way that cannot be readily achieved by biosynthetic means, and potentially allow large scale and commercial synthesis. It is obvious that nature doesn't provide us molecule to have drug available to serve so many people. So we have to develop chemistry to make the molecule. You would know that in 34 years or 36 years of this, because this is 2014 and now we are in 18, so you can add some few more years, almost, let's say it's, in 4 years we have 1600 new drugs, which can be all synthetic, all these things, and out of this 58% are natural products. So if you add natural products chemistry, the most of the drugs comes out from the natural product molecules. Trend is also that if you see here, natural product based drug discovery was like here, in between was a flip, and now we are again growing. That means
natural products are coming back as a drug. Now that is the reason why natural product synthesis has to be taken up. The targets, the proteins or the enzymes, they interact with the three-dimensional molecule. So far, last you can say 10-15 years, most of the people are making very flat molecules for drug discovery, and that is not recognized easily. Well, it's a fluke that you can find some molecule to discover a drug, but natural product-based drug discovery is coming back because all natural products are three-dimensional structures and easy for them to bind with the targets. And in this lecture today, I will present some synthesis of natural products and one concept which we have been developing in our group to discover a drug. So just I will quickly go through this, and once again I will display this molecule, and you will see that it's very complex structure. But now I cannot tell you in this lecture if I have every molecule has a different synthesis. Then it will take a lot of time. Now what we have done, we looked at all these molecules synthesis through a common intermediate, and what strategy or what approach we have for this synthesis is like this. Now if you look at this molecule, all these molecules contain a basic scaffold which is aza bicycloskeleton, which could be spiro, which should be like this or this. Now then if you have to think of a synthesis, innovative synthesis, then what you have to do is start with this. Think that you have inexpensive starting material, you make something and make this bicyclo alkanes, and from here you can make this molecule. Furthermore, for this, we thought this may be the ideal molecule to start with, which is a very inexpensive, very simple molecule. Why we have is the following, right? You have a Michael acceptor, so you can functionalize here very easily. It's a bicyclic system where you can control high distereoselectivity because of the phase selectivity available to the molecule, and ring extent, you can break the ring and have completely different structures, and easy to synthesize in a chiral fashion in multiple ground. This is the reason we selected this. I will not go to the background how this molecule emerged, but this was something idea would like to explore upon. Furthermore, this molecule also has the structure which can be you break here selectively. You have this kind of molecules, quaternary stereocenter. If you have this RR group, so you have this or this one, or you make this molecule. And these are all skeletons. Here the bicyclic ring structure, and also you have spiral ring system for this. Now, how do you make this? As this is small molecule, and you think of a chemistry which has been developed in our group is a desymmetrization of this very simple structure to make this structure, and this can be done through a simple mechanism, this cycloadduct, which is a 3+2 cycloadduct of pyrrole and this acetylenic disulfone compound. You desymmetrization using this diol through this structure. I won't give all the detail. You make 100% diastereomerically pure compound, get rid of this protecting or this acetal group, and you will have a chiral structure. Since this is available in the market, both enantiomeric forms R and S, then you can make both, and you can make natural product in both enantiomeric forms. Now coming to this, everybody knows emergency alkaloids, and let's begin with this. this structure, which is a desymmetrized molecule, can be converted in these two structures very easily, and from there we can make so many molecules of this. And this is very, in our lab, in first student who joins, his training is given to make this desymmetrized molecule, and in one time the fellow can make 1 kilogram of this compound, and then the synthesis begins. Let's see, this is a complex structure, a 3+2 cycloadhesion of this gives this structure, gracilamine, and this is the structure which I showed you, which is available of this. Now this is a common structure. Not only this gracilamine, you can make a quinine, mesembrin, tegetine, and many other alkyls. Let's begin with this structure, and this structure, as I have shown you, can come from here, which is our starting material prepared in the lab. And I will just show you how simply you can make the compound in all triplet, a coupling reaction, and conjugate addition, ring opening, followed by cyclization to come to this structure, and you can make this common structure for this. Now taking this thing, let's see how do you make this. You make enol triplet, do Suzuki coupling to have this high yielding, and allyl magnesium grignard to have this compound, and 1 carbon truncation by hydroxylation you have this, and reductive amination gives this structure. You have, since two types of alkaloids are there, one is a methylene dioxide or a dimethoxy, so one can make both starting from here. If you start with this, then you can make all alkaloids. Now for this structure you make so many alkaloids here. With this structure you make so many alkaloids. Steps are more or less a simple one. Let's begin, just flash it. Gracilamine synthesis. I won't give details. It's shown here. 2 quaternary stereocenters. Difficult to make quaternary stereocenter in a total synthesis. And we make this structure here. It's very simple. You make this. When we started the synthesis, the absolute configuration was not known. The molecule was isolated, the structure was given, but absolute configuration was not known. So we started blindly that let's see, first do the synthesis and decide what is the absolute stereochemistry of this. To begin with here, a bromination is here, and we do formylation, then reduction here to get rid of the tosylative group, and protection of this here. Allylic hydroxylation, have this structure. Now this is not the right stereochemistry. I will not give detail. We tried to continue the synthesis like this. We got a wrong compound. So we inverted here. So this is stereochemistry here, and this here oxidation. In this condition, it gives you ketone, and removal of this PMD here to give this compound. What is next is there that take leucine ethyl ester to make this azomethane allyl intermediate, heat it in the toluene to get this compound, deprotection, and methylation, and methylation gives mature product. By the time when we were doing synthesis, one of my laboratory caught fire, and the students had almost 1 year time, no time research in that lab. In the meantime, so many syntheses came, and when our turn became to complete the synthesis, we found out this was a wrong absolute stereochemistry. So the right plus molecule was synthesized by 2 or 3 groups, but we synthesized was the wrong enantiomer. But anyway, the synthesis, we also have the strategy, like I mentioned, that if we start with the other enantiomer, we will get the right stereochemistry. Then I will just go through quickly that this structure here, you simply remove this here and hit with the paraformaldehyde, you will get this structure. reductive elimination of this, we get this structure. From here, two natural products can be synthesized. The trinene, this is the simplest synthesis you can say for trinene and amberline. That here simple allylic hydroxylation with this compound and dihydroxylation to this compound. So we can make very short synthesis of this natural product. Some more very simple things. It's the same chemistry. I won't go through more. So you make this mesembrine, and also from you can make oxomolatine and molatidine, this compound. So very simple starting material. You can make many natural products are biologically active in a large scale. Then we moved on with the same structure. There are very important alkali. They are called stannine and tuberostemone. Why this structure is very important for organic chemists? That they are used or they are found to be active in neurodegenerative disorders like Alzheimer's and Parkinson. That is why they have attracted a strong attention for organic chemists to synthesize, to be available for biological testing. These molecules are present in very small amount in natural product. So they have to be synthesized and further tested to be brought into for the use for the humankind. Now we looked at this structure and we started synthesis. I will show you both the stannine and tuberostemone through this structure, and I will just simply say that this is our structure. From here we could make this structure and this nucleophilic addition, which also opens this structure, which gives this compound, and this is our functional group transformation to lead to this structures finally. Now let me show you real chemistry rather than showing you retrosynthesis. It's like this. We have this compound. This compound is here you have seen ketone, and I won't say this is a simply conversion of that CO to this compound. So this is optically active compound. You react with Grignard reaction and cleavage. Sorry. This reaction and gives you this here naturally. We originally thought, I'm sorry, here should have been H is missing. We originally thought that if we have a bromo or a chloro, it will in situ cyclize and give you this compound. But it didn't happen. So that is why we had to protect mesylate here, and we have this compound. Now here we get rid of the mesylate group and then cyclizes here and oxidize allylic things to this structure here. Now why we have to do that? Because we have to introduce stereoselectively, which has to be trans to this, and because this will direct the stereochemistry here, and we enolize this and reacted with to get this compound in a complete stereo fashion. What is the remaining is to be done is that you can electronize, which I will keep it later, and we have this structure. At this stage, we remove the SO2-PH group, which is shown here, and since the natural product here, the ethyl group, now ethyl group here also has to be introduced stereoselectively, and we did this reaction, ethyl magnesium bromide in the presence of cuprobromide, and we got this structure. Now, if you see originally if we had thought a conjugated addition and trapping of this enolate by oxyazurine will give you this hydroxy group, which has to be opposite to this. But it did work here, but the yield was not very good. So we went two steps. We first got this compound, then enolized and used Davis oxyazurine to this compound. Now what is there? This ring has to be made. I will not show you all the failures. There were a lot of failures. Finally we succeeded. Protect this by acetic anhydride and intermolecular aldol reaction to get with this compound. What is there? To add here a methyl group, and he added a methyl group, first adding iodine here and a steel coupling to have this compound here. Now we have made this compound here. The student is working needed to be cyclized and reduce this double bond, and this structure, this ketone, if you reduce, then it is stenine, and